We'll be presenting jointly today. Myself, Gabby Daniele, I'm Chief Strategy and Marketing Officer at CoreTigo. Thomas, please.
Yes, and me, Thomas Roth. I'm head of business development at Röhm and responsible about the iJaw project.
Okay, excellent. So I'll start off, and I think actually, hearing these past presentations that were just presented by the colleagues here is great, because it serves a lot of background for what we're going to be presenting, which is actually going to be a case study. So today we'll be reviewing a case study of an intelligent tooling solution that was developed jointly by Röhm and CoreTigo. Our goal is to explain to you the value that can be achieved by enabling more digitization on the machines themselves on one hand, but on the other hand, the importance of the convergence between OT and IT that's going to be demonstrated here. So I want to start off with the digital transformation that we're all experiencing as part of the Industry 4.0 revolution. The consumer behavior, which is demanding more customization, in addition to global supply chain shortages, which we're all experiencing these days. They're both driving the manufacturers to be more adaptive than ever. And all this without trading off the capacity and actually even demanding to increase the throughput and the capacity. However, what we're seeing is that most manufacturers, they're also suffering from issues such as lack of skilled operators. Machines are becoming more complex to operate, and also there's lack of flexibility and modularity on the machines, which is leading to non-optimized machine performance. It's leading to inefficient and expensive maintenance operations, and also a decreased throughput and overall capacity. So basically what we need to do, we need to see how we can get our machines to be able to do more, okay? But they need to be more flexible, more independent, and more self-healing, or we can say self-optimized on the machine itself. Now, all this can't just be done by having some dashboards or by ongoing manual tuning of the machines, that can be done by operators that are changing their shifts continuously. This transformation has to be done from the ground up at all layers, and this is what we want to show you here in this solution that we're going to be demonstrating. Now, as Gordon was talking about iLink Wireless, a key component of this solution that we'll be presenting is actually iLink Wireless. iLink Wireless serves as the communication means for this solution, and it's actually creating a paradigm shift, because it's breaking the limits for machine connectivity solutions and machine connectivity applications. As mentioned, iLink Wireless is actually an extension of the well-known iLink standard, so it's an official global IEC standard. It was designed specifically for factory automation and the needs of factory automation and the harsh environment of factory automation. It has cable-grade reliability, and this is literally 1 million times more reliable than any conventional existing wireless solution. So you take Wi-Fi, Zigbee, Bluetooth, so it's a very high reliability that's pretty much cable-grade. It has low latency, which enables it to deal with high-speed and motion solutions, and also scalability to support hundreds of devices in a machine area or a work cell area. Now, if we take all this, this actually enables us to do many actions while we're in constant motion. And Gordon showed some of the examples also, and doing all this at very harsh conditions. So this enables machine connectivity pretty much anywhere, even in places that were not possible before, where we were limited by cables or by complex layouts. And in turn, it also enables us to create smarter and more intelligent devices at the edge. So it's not just the communication, but it's also the intelligence now that we're applying at that edge that is being communicated. Here, what we can see actually is that this solution can be applied anywhere in the factory, where you need machine flexibility along with high-speed solutions. For example, on the left-hand side, you can see the independent mover transport track systems, or carousels. These are used quite a bit for packaging machines. So now, on each mover or each shuttle or independent kind of component, we can actually connect devices such as grippers or vacuum pumps and control them. So this is not just about monitoring or sensing. It's also about controlling, both actuators and sensors. Other examples include robots or collaborative robots, where you have the end-of-arm tooling that's also limiting the flexibility, it's limiting the tool changeover. Rotary tables and rotating tools on CNC machines, grinding machines or milling machines on the right-hand side. That's also an example of places where you have very high-speed turning components, rotating components, also in very harsh conditions. And this will be our focus today. Our focus today will be on the CNC machines and how we're enabling intelligent tooling in the most precise manner at the clamping point, at the tooling point itself, while it's machining. So again, this is something that cannot be done beforehand. And at this point, I'll hand it off to Thomas to talk about the intelligent clamping solution.
Thank you, Gabby. Perfect. I just want to introduce you a little bit into the clamping industry, because I guess we have heard a lot of IoT and data at the moment, and not so much about use cases and how the systems are applied. So what you see in the picture here down is a system what we sensorize right now. The golden thing in the middle is the machining part, is the workpiece, and on the left side, which the picture shows, is the turning chuck, and are the jaws which fix the workpiece into the chuck. So, and this is what has never been sensorized before. So nobody knows exactly what clamping force is there used for holding the workpiece. And also we are transferring data at a high speed rotation in harsh condition. We have water there, we have cooling liquids there, and it's a really great leap, I can say, in sensorizing elements in the clamping industry. Okay, we can go to the next. Gabby, please. Thank you. Okay. What you see here are different layers of our, how can I say, construction. We have the smart device. At the bottom of the chart, you see the chuck on the left side. Yes, thank you, Gabby. And the smaller things on the chuck you see are the jaws I mentioned before, and this is what we have sensorized. And on the right side, you can see how we did this. We put sensors in the jaw so that they can register and measure the clamping force that is how can I say, at the workpiece. And this data is going to be transported to the next level via a master or a gateway to the cloud. Or on the left side, where you can see the PLC. This is a little bit a different use case of the two right pictures, is you can transfer the data directly on the PLC of the machine. For example, DMG Mori is doing it right now. They have applied the system and introduced it right now at their show, at their open house, which is taking place this week. They have integrated our system in as an option in their machine, and so we made a great step forward in the application, the usage of the system. Data is going to be transferred in our aftermarket solution in the next layer in the cloud application, so that we can make the data that is measured at the clamp, at the jaw, is made visible. And the visualization of data makes the usage possible. And we derive several use cases from the sheer visibility of the data, and improve processes, improve handling, improve security levels, make it more easier for the operator to work with the system. Okay, next, please. This is one of the first examples what we see on the right side. You see the chart, and we see it's a little bit small, but columns, the 3 columns that are mentioned is machining. Then you see the hill of the graph. It's a stopping, and then you see the cooling of the system. If we have if we see what force is being set to the workpiece, we can derive measures. In this case, for example, we also can measure the temperature, and we can see that the temperature at the workpiece, for example, gets higher. And if the temperature at the workpiece gets higher, the material expands. And if the material expands, the clamping force is certainly getting higher. And this is what we see there. And if we do not want a deformation of the workpiece, for example, we have to reduce the clamping force, or we have to add cooling liquids. And this is one of the cases which is only possible by the visualization of data. So the sensors and IO-Link and the visualization of data on PLC or on cloud systems make it very helpful to produce better workpieces and to reduce downtimes, for example, to reduce security issues, and to make the process more easy and more reliable. Next one, please. So the core of our system is, as I mentioned before, the measuring of the clamping force in real time during machining. And this is really important. Real time during machining. Before, it was possible to measure the clamping force without or not in the machining process with some tools. But this is not the most important information. The more important information is the clamping force during the machining process, and only cable-less IO-Link systems enable this. For example, what you see on the right side in the blue chart, you can see that the curve, more or less, the trend of the curve is decreasing. And this means the clamping force is decreasing via time. That means I have at the right time the information that clamping force decreases, and I have to intervene and to enlarge the clamping force again, so that I do not have any problems during the machining process. When I know this, that the clamping force is decreasing, I can set a service, for example. I can plan maintenance. I can plan a repair, and all these things I can do in advance, so that I have planned downtimes, which are the better downtimes and which are the shorter downtimes. If you're working in machine tool industry, you know what I'm talking about. On the right side, the red diagram is showing some differences in the pattern. Differences in the pattern are indicators for deviations in the machining process. And in our example, you can see at the picture on top of the red diagram a small blue circle around the tool, and this tool is broken. If you work with a broken tool on a workpiece, the quality of the workpiece certainly, obviously, is not very good. And the diagram and the pattern of the diagram can show it to you when you identify that the pattern of the piece is different than the piece before. If you do, for example, 100 same pieces, you have, if it's perfect, 100 same patterns of the data structure. And if there is one or two different deviations and differences, you can have a look at these. You can identify these pieces, and you see what went wrong. You can see that immediately. Okay, we can go to the next slide. The precise setup the most of the time you put your workpiece by hand into the system, and you have to put it very precisely into the chuck and the jaws and put the piece into the machine. And sometimes it can happen that the piece is not at the right angle in the machine, and there is some, how can I say, run out, some non-circular run out of the machining of the workpiece, and this is certainly not optimal for the symmetry of the tool if you are, for example, turning. If there is a deviation in the measured clamping force, I also can identify that there's something wrong and have a look at that, and can go deeper into the system and fix, for example, the wrong or adjust. So that's what I have to say, and I can adjust the workpiece in its right place. Okay, thanks. Next, please. Documentation. Documentation, and I add the analytics a little bit to that. What I get, we have heard before, is a data stream, a non-ending data stream during machining of my clamping force into the cloud and into analytics systems, for example. I can use these data streams to have certainly a look at the clamping force right during the machining process, but I also have to could have a look at these forces afterwards. If I have to find out if some of the pieces, for example, did not been milled or turned very well, I can also see it in deviations of patterns of the registered or of the how can I say, stored and measured data. What I can also do is I can see downtimes, for example. I can identify how long downtimes during machining process were when I measure and record all the machining data, because it's fluent, it's permanent data. And if the system is not running or not turning, there is no data. So I can see the downtime of the machine, for example, from far away, because this is a cloud solution, and I can have a look at this data from my handy, for example, or from the supervisor's office. He can see which machines are running, which machines are producing what data, and if everything's running right. He is looking every time at the same curves, for example, and if something's going wrong, he has deviation in the pattern. And with this information, you can optimize your process, for example. You can optimize your complete production process by identifying downtimes, by identifying the reasons of downtimes, and you can do some analysis on the clamping process itself. You can see the length, the complexity, and a lot of information you can use to optimize your process. And certainly the documentation, at least, is also a very important thing, because so far you couldn't prove the machining quality of the workpiece, for example. And if you need to prove that, what sometimes could be interesting, or could be the case in maybe aviation industry, where you have to provide very precise and optimal produced stuff. There might be the how can I say, the case that you have to prove if your part that you have delivered to your customer was produced in the right quality. And with the stored data, with the documentation of the data, you can do this. Otherwise, you weren't able to do it. It was just a visual, more or less. Certainly, there are instruments how you can check the quality of your workpiece, but this is an additional channel of information where you can get the information how the workpiece has been produced. Okay, Gabby, thank you. The next one, please. This is a little bit similar to what I have mentioned before. If you put a workpiece automatically into the system, you can have a look at the data, and if you know how the data has to look, if the workpiece is put right in the machine, you can compare it with the information you see here, and if the diagram, the curve, has a deviation or a difference from what you need to see, you can see that the workpiece is not put successful into the machine, and you have to react and correct the issue. So there is you save time because you don't have a security breach, for example, or a breakdown, because you can see in advance what has to be corrected, and you can install the workpiece in a perfect manner into the machine, and nothing should happen during machining then. Thank you. Next one. If we sum up the advantages, what we have with the visualization of data of clamping forces, you can do really a lot with that. We improve safety, for example. I mention again, if the clamping force declines, we can make it visible, and you can stop machining, or you can plan maintenance in advance, and therefore you are in average in your process much more safer. The right one, predictive maintenance, has how can I say, has a connection to that what I mentioned before. You see declining forces, and you can plan a maintenance. You can get higher quality because you see differences in patterns of the data, and you can reprogram more or less if needed your machine. For example, you can adjust machining process with the backup of really measured data. Automatization is possible because there has no one to be there to supervise, to watch the process. Traceability is how can I say, the storage of the data, the analytics possibility. What do you have? You reduce the downtime, and you optimize the machining and the machine itself by using it. That's it from my side. This is a short about our showcase. We could, if you go deeper in details, feel free to contact us. We can go deeper in detail, but at this point, I think it's enough just to show how we bring data at the right time, at the right place. As Naresh said in his introduction, make data visible and use the data for improvements.